So last time we ended with this this schematic, which is basically showing how silicon chips are manufactured. We saw that video last time too, so I'm not going to spend too much time on this other than to say that you start off with silicon. The silicon is melted down in a pot, which we'll just talk about next. It creates this thing called ingots. Now the thing about this ingot is that it is single crystal silicon. Okay. It is a crystalline silicon that has a low amount of defects on it. This ingot is then sliced up into small pieces called wafers, and the wafers, then there's a 26-step process. Actually, more than 100 steps if you include all the intermediate steps that are used to convert this bare silicon wafer into a wafer that has a microchip microprocessor built onto it. So it's a series of steps called photolithography, where you optically define where you want your transistors to be. A transistor, if you remember the picture that we saw earlier, it consists of a p-type region and an n-type region, and there's a gate region for those of you who remember from Electronics 1. So when someone does what's called electronic circuit layout, you're literally indicating which regions are going to be P, which regions are going to be N, where the gate is going to be, the source and the drains are going to be. And you do that for each transistor on your chip. Of course, you don't do that one at a time. It would be impossible to lay out 40 billion transistors one by one, right? So you have computer-aided tools that allow you to, if you define an AND gate as these two transistors, then or a combination of transistors, and those designs are just copied and pasted into more complex things like arithmetic logic units and whatnot. But the message is that you are defining where the transistors are going to go, and those regions are defined through processes called photolithography, diffusion. They use things called wet etching, dry etching, and things like that to define them. We're going to be talking in detail about those later, so we're not going to go into that now. When the wafer is completed, you usually have hundreds or thousands of microprocessors on there, and then it is sliced up, sliced vertically and horizontally to form these individual chips. Those individual chips are bonded to a printed circuit board, which is ultimately placed into your computer. It's also placed in a package to help keep it cool. I just want to touch on the first step of the process, and let's hope this video, I think it worked last time. This is the process on how silicon wafers are made. In fact, just to save time, maybe it's better if you just take a look at this video on your own, because the Intel video that we looked at in class last time showed the basic idea. You have basically a pot, and in that pot you put a silicon material, polysilicon material, and then you heat up the pot and then you rotate it. Okay, the schematic of it is right here. Polysilicon is melted into this pot, and then you put in a seed crystal. Now, in order for you to create crystalline silicon, you actually have to start off with a small amount of crystalline silicon. Okay, it's kind of like a chicken and egg kind of thing. You have to have some crystalline silicon before you can make more of it. I recently learned how to make yogurt. I don't know, does anyone made yogurt before? Okay, some of you. You know how you need to have a little bit of yogurt before you make more yogurt, right? Anyway, so you need to have a seed crystal before you can make more crystalline silicon. This seed crystal is dipped into the melt of polysilicon, and it's rotated very gradually. Okay, the rates at which it's turned is very well controlled. The temperatures of the chamber is also very well controlled, and you basically pull out this seed crystal. As you're pulling it out, the silicon atoms deposit on the side of the seed crystal, also depositing in crystalline form. And as you pull this cylinder out, the cylinder is called the ingot. You're rotating it in the meantime, and it's the atoms from the polysilicon melt are basically depositing on here in crystalline form. And at the end of the process, you have this ingot, which is basically a big piece of single crystalline silicon. Okay, and you can see that some of these ingots here can be quite large. This one's like probably 6 or 7 feet tall, about the size of a little bit taller than this person here. The size of these ingots have grown as we have more and more need for the semiconductor manufacturing. They used to be quite a bit smaller, but now the semiconductor industry is a very large industry. Thousands and thousands of chips, not thousands, millions of chips are going out all over the world. So they have scaled up these processes accordingly. This process is called the Trotsky method, and it is a very important process because without single crystal silicon, we wouldn't be able to get the repeatable properties that we need for semiconductor devices, reliable semiconductor devices. So with the silicon wafers, after they are sliced up, they are usually doped N-type or P-type. If we go back to this slide here, when we introduce this melt silicon, we actually can do the doping at that time. We'll talk about what doping is later, but for the moment, I'm going to say that you can have two types of silicon, or you can have N-type silicon, which is doped with column 5 atoms, and you can have P-type silicon, which is doped with column 3 atoms. Okay, when you introduce those impurities into the silicon, it changes the properties of the silicon, and in some cases, it can make the silicon more conductive. If you have an undoped semiconductor, then it's less conductive. We'll talk more about that later, so don't worry about that now. These wafers typically are circular like this, and they also have one or more flats on different parts of the wafer. This is called a wafer flat, just a portion where it's the circular curvature is instead you have a straight line here. These are examples of wafers with flats on the sides, the top and bottom. The location of these flats tell you what type of wafer it is. Now if we go back to this slide here, if you recall, if you have crystalline silicon, imagine this as a three-dimensional volume of this crystalline silicon. The ingot is a three-dimensional volume, and when you slice that ingot, the angle at which you're slicing will determine what face of the crystal is exposed. If you cut it horizontally at a 90-degree angle, then you're going to have the 100 plane exposed. If you cut it at a 45-degree angle, then you may have the 110 plane exposed. And if you cut it at a different angle, you may have the 111 plane exposed. So almost all the wafers, most of the wafers that are sold are 100 type wafers. Okay, you'll have a problem in your homework where you calculate the atomic density of atoms on the 100 plane. I will post the homework today after class. Okay, so you can work on it over the weekend. We'll have our first quiz on Tuesday. So the different types of wafers, you can have P-type wafers, you can have N-type wafers. That means what type of doping it is. You can also have wafers of different crystal orientation, 100, 110, 100, and then 111 wafers, and so on. Okay. Any questions on this? So the wafer flats describe the crystal orientation and whether it is P-type or N-type. Common diameters for these wafers, so, it includes like 50 millimeters, 76 millimeters, 100 millimeters. So you can see there's many different sizes available. And one of the trends that, if you notice, from the 70s until now, is that you see that the size of these wafers are growing. So one of the questions I want to ask you is just why are the sizes of the wafers growing over time? Yes?
More transistors.
Yes, you could pack more transistors on the wafer. Exactly. Let me ask another question then. Well, first of all, why would we want to have more transistors on the wafer? We talked about that last time.
Then you can get more chips on it per wafer.
More chips.
More quickly.
Right. Right. More chips on it means more money, right? For the manufacturer. So it really is an economic reason. So that being said, then why didn't we just start off with gigantic wafers back in the 70s? Why did it take this long? Why did the wafer sizes grow over time? Why don't we just have large ones to begin with? Yes?
The need increased per wafer.
That's part of it, yes. The demand for semiconductors, our appetite for semiconductor devices and cell phones and laptops, and it's just increased voraciously.
Capabilities weren't there initially.
Yes, that's the other thing. The capabilities were not there initially. In order for you to work with some of these huge wafers now, some of these like 12-inch wafers that some of the fabs use right now, you have to have extremely uniform manufacturing processes so that the chips on the upper right corner of the wafer are just as good as the chips on the bottom left-hand side of the wafer. So all the equipment in your semiconductor manufacturing process has to have very uniform deposition parameters, uniform etching parameters. It requires a lot of engineering work. And over the years, the fabrication equipment has gotten better, so you can have uniform deposition, uniform properties throughout the entire size of the wafer. Okay, how much this will continue it remains to be seen. Transistors are getting smaller and wafer sizes are getting larger. So what happens is then that the cost to make a single die, single microprocessor chip, goes down dramatically. So microprocessors that would cost hundreds of dollars back 20 years ago might cost us a few dollars now. Okay. Good. So the first part of it is that the size of silicon wafers are growing, and then transistors are also getting smaller. And these are some of the slides that were published by Intel back in, I think this was back in 2012. So things have even developed more since then, but this just gives you an idea. This portion here, this picture here, shows the 4004 processor back in 1971. And this one shows the third generation Intel Core processor in 2012. So the chip on the right is 4,000 times faster, 5,000 times less energy per transistor, and 50,000 times cheaper per transistor. Okay, this all has come from miniaturization. So when you make the transistor smaller, it ends up consuming less power and ends up taking less space on the die, so it's cheaper to make. And interestingly, it also becomes faster because the amount of time it takes for the electron to move through the device is less. Okay, so all these things have folded into like this Moore's law that we talked about in class last time. Really a remarkable trend, both scientifically and in terms of the ability of industry to keep up with this prediction that Gordon Moore made. Some of the technologies that they've had to adopt in order to maintain Moore's law. I talked about this in one of the first classes. At the beginning, it was easy to improve the performance and all these things of the transistor just by making the transistor smaller. Okay, the operational parameters weren't affected drastically. You just make the device smaller and it worked. However, over time, maintaining the performance of the transistor, I'm talking about the on versus off current, the power consumption, the ability of the transistor to behave as an ideal current source in analog, when you're using it in analog circuits. The early voltage of the transistor, these different parameters, the threshold voltage, maintaining those parameters as you scale the size down, it actually becomes tricky. So Intel adopted different technologies. For example, they use strained silicon since 2003 to improve the mobility of electrons within the device. That helps improve the speed of the device. In order to maintain good threshold voltages, they started using a high K metal gate. Is that Darth Vader? I could have sworn I heard Darth Vader in here. In 2007, they started using high K dielectrics. Like the gate material was made of new materials that had a high dielectric constant. And starting in 2011, the slide I showed last time, they started using a tri-gate transistor, which is a three-dimensional type transistor, so that you could control the current in the on and the off state better. So you had better control of when the transistor was on versus when it was off. So Intel has had to do a lot of innovation in this. They've scaled down the sizes from 10 microns back in 1971, In 2011, it was down to 22 nanometers, incredibly small. You think about that the size of atoms are on the order of angstroms, which is just an order of magnitude less than that. So you're getting down to transistors which are not that much bigger than individual atoms. 22 nanometers, down to 14 nanometers in 2013. And the things that are in research right now are transistors that are getting close to 10, 7, and even 5 nanometers. We're not quite there yet, but these technologies are being heavily invested in. They're heavily researched. So this trend is expected to continue, although it might be at a slightly slower rate than what was originally predicted, or the trend has been over the last 30 years. Any questions on Moore's law? Any questions on crystal structures? I want to make one correction to the notes that Justin pointed out. Thank you for sending the email. Yesterday in class, Tuesday in class, I mentioned that metals are amorphous. All right, and that was a mistake. Sorry about that. The metals are actually polycrystalline, and so what we were talking about, just to remind you, is that we were talking about that metals have this ductile nature, ductile and malleable. Okay, in order for a material to be malleable, the crystal structure has to change, right? Because the atom, the atomic structure has to change when you bend the material, right? So the ways that metals do it, they're not quite amorphous. They're actually not quite crystalline either. They're polycrystalline. What happens is that in metals you have those regions of crystallinity, and when you bend the metal, those regions of crystallinity actually slide up against each other. If we can just jump back to the slide here. We were talking about crystalline, amorphous, and polycrystalline materials. In metals, you have these regions of crystallinity, and they're separated by grain boundaries. When you bend the metal, these two regions can actually slip against each other like that, and so that material can deform that way. Thank you, Justin, for clarification. So, any other questions on this module? All right, great.
Just have one quick question.
Yes.
So like the Intel i7 used to run like around $200 or so. How much does it actually cost for them to make one?
Very good question. The question is, how much does it cost for Intel to make an i7 processor?
It's like, I know it used to go around 200. I don't know what it is.
Yeah, the cost to buy it is around $200, but I can only estimate, but I can imagine it's quite a bit less than that. Their markup
So
is quite high.
Fairly cheap to make them.
It's fairly cheap to make them when you make them in bulk. If you were to just make one processor, it's quite expensive to do that. But the thing is, whenever you go through those 100 whatever manufacturing steps involved in the CMOS process, you end up with hundreds or thousands of processors. That's the whole reason why you go to this batch manufacturing process. A lot of it used to be done by hand before. Now even the handling steps, moving the wafers from machine to machine, it's all done by robots now as much as possible. Because these rooms have to be maintained in a very, very clean environment. When the transistors are 10 nanometers, a fleck of dust, a piece of dust might be 1,000 times larger than the transistor itself. So you can imagine that in the foundries where these things are made, you can't have any pieces of dust. And so they have these things called clean rooms. We have one here. Ours is a class probably 1,000 clean room. That means there's 1,000 particles per cubic meter or cubic feet. I can't remember which one it is. In these types of situations, they have class 10 clean rooms or better to prevent any type of dust particles, any type of contaminants from getting into the wafer. Yes?
For each wafer, so are there like multiple microprocessors on each wafer that when they design or do a design on the wafer? Like a Core i3 over in this corner or i5 in this corner?
Oh, so the question is, are there multiple designs on the same wafer? Most often not.
Okay.
They'll do one type of chip design and then they'll just repeat that same design over the entire wafer.
Okay.
They'll have another wafer run that's being done for the i3 processors.
Okay.
Sometimes, and I've heard about this, is that in order to save money sometimes, if they have like a high-end microprocessor that runs at 3 gigahertz and another microprocessor that's similar, but it runs at a slightly lower clock rate. Those are actually the same chip. Intel just sells one as being a higher clock rate.
But how do they determine which one will handle a higher clock rate?
They actually
Isn't
do.
the clock rate more about like heat dispersion than anything?
So the question is, how do they determine which ones have a higher clock rate? All these microprocessors, if you remember from the video last time, they're tested one by one, right? So when they're doing the testing, they actually run some a regression tests on them to determine what the clock rate of the device is. The reason why some chips may have different clock rates than others is because just due to manufacturing variations. Okay, so they might they'll choose the ones that where they clock out at higher rates, and they'll sell those at a slightly higher price. The ones that test at slightly lower clock rates will sell at a different price.
Nowadays you have like the multiple core version that's if one core is broken, you can still seal that.
I'm sorry?
You have like a multiple core version of the processor that if you lose one core, you can still have like enough power to proper set.
Oh, multiple core processors.
Yes.
Yes. So Intel now has like multi-core processors, which essentially is like multiple microprocessors on the same die. It's good for multitasking. So like a lot of the computers now like have quad core. Some phones have octa-core processors, dual core processors, things like that. So the reason that they're there is less for redundancy. It's more for being able to multitask. Another thing that happens is that you know how Intel has the high-end microprocessors and then they have the Celeron ones? The Celeron microprocessors have less cache on them, like less on-chip memory. So I heard about this. I haven't looked into it myself, but one of the engineers told me that something Intel does is that they actually put the same design on all of them, and they fabricate all of them. But at the end, in the Celeron processors, they actually burn out some of the memory. So they actually make the memory, but then they burn it out. Why you would do that? It doesn't make sense to an engineer, but I guess to the person with the business hat on, it makes sense because you're selling to different markets.
Similar to that too.
I'm sorry?
We do stuff similar to that too.
Freescale does too?
Yeah, so like,
just as evil. No, just kidding.
Yeah,
No.
like we could sell you like a 2 meg part, which may actually have 4 meg on it, but you would never think to look, right?
It's been burned out.
Because well, it may not necessarily be burned out, but for us to do a whole session of 2 meg parts and another whole run of 4 meg parts,
Exactly.
it's just easier to do it all and be like, well, that's what this is. And the deal is if you can use it, like let's say you discover it's the same thing, but if anywhere from above 2 megs fails, we're not responsible because we still do a 2 meg part, right?
Yeah.
So there's all sorts
Wow.
of stuff.
So that's even more interesting. Like the capabilities there. You just
Right. And Intel may do something similar too.
Well, when we were talking about the overclocking, right?
Yeah.
They you know, processors, the spec that they give you, if they say it's 2.5 gigahertz, you might actually be able to run it at a higher clock rate if you keep it cool.
Well, yeah.
Which is why a lot of gamers have,
Like one of the 810s, the 810 6800, someone actually used a liquid nitrogen cooling system and clocked it to like 7.2 gigahertz.
Wow.
You
That's
can probably
remarkable.
go higher if you use the liquid helium cooling system. But.
That's really amazing. That's quite amazing. So a 3 gigahertz processor clocked out at more than 7 gigahertz.
7 to 8.
That sounds quite amazing, actually.
But it was up there.
I mean, that's really surprising. But what happens is, we'll talk about this later when we get to the next module. But temperature actually slows down how fast carriers can move through the device. So when you bring down the temperature of a device, you're reducing something called lattice scattering. And so electrons can travel faster through the device, and that's why the microprocessor operates faster at cooler temperatures. However, that's only the tip of the iceberg. We'll talk a little bit more about that in the next chapter. All good questions and comments. It's great to have a semiconductor engineer in the class. Yeah.
Just real quick with the ingots, so it can be designed to cut along the 100 or the 111 you showed.
Yes.
Now, did they actually manufacture the ingots so you can still just cut circles, or do they actually have to cut it at a different angle after the fact? It's fully seen.
Yes,
complete circle, right?
that's a good question. Are the ingots manufactured in a way that you can still cut orthogonally and get a different plane, like a 1-1-1
So I've
plane?
never seen an oval version or whatever angle you'd have to cut.
Yeah,
in a wafer.
I think it. Now this is something I'm not quite sure, but I imagine that maybe if you introduce the seed crystal in a different angle, then the orientation of the ingot
Okay.
would also be at a different orientation. I will say this is that the 1-1-1 wafers and 1-1-0 wafers are much less common. Much less. Almost all semiconductors are manufactured with 1-0-0 wafers. All right, good. So let me just stop this recording. We'll start a new one for the next.